And our next talk is by Josiah about white dwarf mergers.
So today I'd like to share with you our emerging understanding of the role that double white dwarf mergers play in the formation of single white dwarfs. And I want to start that by using this schematic HR diagram to tell you the story of merger and its aftermath. And so the picture is that we've started with two single white dwarfs going down the cooling track, and they're in a tight binary, brought together by gravitational waves. Unstable mass transfer begins and leads to a merger. Now, in some cases, we think that that merger then triggers a thermonuclear explosion and potentially produces type 1a supernovae. And so those objects leave our story. But for those that continue, they enter into a luminous phase where they're radiating energy for tens of thousands of years or more. But eventually the objects then begin to cool. And at that point, as things begin to become degenerate, if the objects are above the Chandrasekhar mass, then they may collapse to form neutron stars and again leave our story. But otherwise, they continue down the cooling track and return to being white dwarfs. And now you've taken your two white dwarfs and replaced them with a single one. And I mentioned this evolution because it's important, because this evolution influences the mass and the composition and the rotation rate of the remnant white dwarfs. And so it's important to think about this evolution in terms of thinking about what are we going to see in terms of white dwarf merger remnants on the cooling track. And so I want to begin talking about the luminous phase, because there are classes of objects that we see that we believe are this luminous phase in the aftermath of mergers. And in particular, when we have mergers involving one or two helium white dwarfs, you set up a post-merger structure in which you have a sustained period of helium burning powered stellar evolution. And we think that's the formation mechanism for the single hot subdwarfs, and in particular also for the R Corona Borealis stars. These are long-lived helium-burning stars formed from white dwarf mergers. But even in the absence of sustained nuclear energy release, you still have this luminous phase because merger remnants basically have to radiate the gravitational potential energy that was liberated in the merger. And that means characteristically, you have an object sitting kind of near the Eddington luminosity for something like its 10,000 year thermal time scale. And I think one of the most interesting objects to emerge in the last few years is this object WS35, which was published by Farmad et al. In Nature a couple of years ago, as a massive white dwarf merger product in potentially before final collapse. And so what is this object and what makes it weird? So in particular, this is an infrared nebula here, kind of a parsec scale. Yes?
Really sorry to stop you. There's a black box on the top of your screen that's covering some stuff.
Okay, yeah, unfortunately I had to stop, when I stopped the share, it did not go away. That's why I stopped the share when I first started. So let me try that again. It wasn't here when I tested.
They're getting bigger now.
Yeah, I know, right? So
usually these come from like other tabs that you might have opened.
It comes from Zoom, and I asked it to hide the video panel, and it has apparently not done that.
Yeah.
Maybe you can share just the presentation and not the screen.
Okay, so let's see. Thanks for letting me know, Ken. Very frustrating. Now the video panel came back, even though it shows as hidden.
You can make it really small. There are controls on top where you can make your video panel to be like a little.
Okay, so the video panel has now gone away, and now what's showing is these controls, the like pause share, new share.
Well, maybe in the interest of efficiency, you could just, assume we can't see it. And,
yeah, here. Well, if we really can't, if in the interest of seeing the slides, I can try to just share Can you see my window here?
Yes.
Okay, I'll share in this presentation view.
Thank you.
Yes, thank you, Ken. Where were we? Okay, so in particular, what is this unusual object? So there's an infrared nebula, and if you look at the same scale in H alpha, you don't see any hydrogen. So this appears to be quite hydrogen poor. In the center of this nebula, there's a Wolf-Rayet star, or an object at least with a Wolf-Rayet spectra, so a hot luminous central star that shows clear carbon and oxygen lines, but again, no evidence of helium, so this appears to be hydrogen and helium free. And there's also X-ray spectra of this nebula, and the X-ray spectrum shows evidence of carbon and oxygen burning products, including neon, magnesium, silicon, and sulfur. And that's all quite unusual, and a white dwarf merger provides sort of a natural explanation for this object in the following way. The picture is that you're seeing something that's kind of 10 or 20,000 years after the merger. Previously, it was in some sort of kind of luminous giant phase where there was a significant amount of mass loss, and that has potentially created this parsec scale nebula. And now things have evolved, and you have a central object of something like a solar mass or a solar mass and a half that's hot and luminous and blue. And in particular, because it's kind of solar mass scale, that kind of explains its luminosity as being something that's intermediate between the typical central stars of planetary nebulae, which have lower luminosities, and say the kind of Wolf-Rayet stars for massive stars with their significantly higher luminosities. And so there's a lot of mysteries surrounding this object, but the kind of broad point I want to make is that there are opportunities for us to catch white dwarf mergers in this kind of luminous phase between the merger and when they return to the cooling track. But I want to take us to the cooling track, and in particular think mostly about white dwarfs there. And so once you've kind of returned to the cooling track, the key question is, how do you pick out the white dwarfs that were produced via mergers? And in particular, we think that white dwarfs descended from double white dwarf mergers may stand out in terms of their compositions, because you've had the opportunity during the merger to destroy additional hydrogen and helium. And so they may be hydrogen and helium poor, and so correspondingly richer in carbon, the next lightest thing. You had a lot of angular momentum in the orbit of the double white dwarf binary, and so that seems likely to create single white dwarfs with rapid rotation. Likewise, the merger gives you a chance to create and amplify magnetic fields, and so this may be a route to producing strongly magnetic white dwarfs. And the ages of these systems are also different, and in particular, they may exhibit different kinematics as a result. And so when you think about looking for white dwarfs with these signatures, one of the best places to do so is to look in the ultramassive white dwarfs, because you simply kind of have produced less of those through single star evolution because of the IMF. And when people do population synthesis calculations, they find, that white dwarf mergers may represent 20% or more of the objects at these masses. And so now I'd like to take you through some of the objects that folks have found in the last few years. So white dwarf mergers, again, they may stand out in terms of their compositions. So Hollins et al. Report a 1.14 solar mass white dwarf with extremely small hydrogen and helium layers, such that the atmosphere is hydrogen and carbon. And this object has the interesting property of also being located in the instability strip. And so there may be potential to use astroseismology to also learn about ways in which its interior composition is unusual or peculiar. Analysis of large samples of the DQ white dwarfs that are carbon rich reveal that the massive DQ white dwarfs really show a distinct kind of abundance pattern in terms of their carbon and helium abundances. So these are white dwarfs that are kind of around a solar mass or so. And that's really distinct from the lower mass population of DQ white dwarfs, where we understand the carbon abundance as a result of dredge up from convection. But these massive white dwarfs really probably have a fundamentally different chemical composition. When white dwarfs don't emit uniformly across their surfaces, then we have the opportunity to use photometry to detect the rotational periods. And that's now been done in a number of systems. So last year, Shirkov et al. Reported kind of quite massive white dwarf above 1.3 solar masses with a 6-minute rotational period. There's the classic kind of 12-minute rotator, again, a 1.3 solar mass white dwarf, J0317-853, that's been known for many years now. Redding et al. Reported a more typical mass white dwarf with a 5-minute rotational period. And there's a white dwarf, again, a very massive one, where a photometric period was detected in ZTF, and follow-up shows that that has a 7-minute rotational period. So we see objects that are much, much more rapid rotators than the typical sort of hours-long period of white dwarfs. We also, again, think they may stand out in their magnetic fields, and the long-known object that I pointed out on the previous slide is also known to have a kind of many 100 megagauss scale magnetic field. And that ZTF object I mentioned on the previous slide is also known to be quite strongly magnetic. And when you start to have fields of that strength, you no longer just sort of perturbatively Zeeman shift the lines, but you move things around and distort things dramatically. And so as a result, when you look at the spectra, the lines aren't often where you think they are, and such objects often end up classified as DC white dwarfs. And so I looked at the 100 parsec sample in the SDSS footprint from Killick, and there are 2 DC white dwarfs listed at effective temperatures of 40 kilokelvin, so much hotter than the usual DCs, and with masses of kind of 1.3 solar masses. And so I'd lay pretty good odds that a follow-up of these 2 systems also would quite possibly reveal massive magnetic white dwarfs that are rapid rotators.
Just one more minute.
Okay. White dwarf mergers may also stand out in their kinematics, and in particular, because they have older ages, because of the longer time scale it took to form the less massive white dwarfs that merged to make the more massive white dwarf, plus the kind of longer delay time that you have of the merger. These systems are older, and because older systems experience more heating in the galactic disk, they show higher velocities. And the plot on the left here shows the transverse velocity distribution from a sample study by Cheng et al. And you can see the tail to high velocity transverse velocities. And they use that to infer that, so again, something like 20% of these massive white dwarfs are descended from mergers. And I've kind of emphasized signal signatures in the last few slides, but we expect white dwarf mergers to stand out in multiple ways. In a recent analysis of the 100 parsec sample in the Montreal white dwarf database, Killick et al. Show 8 of the 25 objects show at least one of these kind of potential merger signatures. And so as we move forward, we want to basically uniformly characterize our local white dwarf samples in a way that we ought to be able to tell a unified story for the merger population in terms of its composition, rotation, magnetism, and kinematics. And so it's really exciting because we're entering into this era, thanks to Gaia, of an increasingly complete and well-characterized sample of the local white dwarf population. And our observations are clearly revealing the significant role that double white dwarf mergers play in the formation of single white dwarfs. And I'm really excited that this growing number of likely white dwarf merger products are going to let us tell a more complete story about the merger-formed white dwarf population. Thanks.
Excellent. Thank you very much, Josiah. We have time for plenty of questions. Brian is the only one right now.
Hi, Josiah. Thanks for the talk. So you mentioned a signature of merger being reduced hydrogen and helium. I guess, and you mentioned this Holland's object.
Yeah.
I guess I'm wondering how any hydrogen survives one of these mergers. I mean, you would think that things are, going to be well mixed and quite hot. And do your models find actually some hydrogen surviving?
Yeah. So if you are able to make small amounts of hydrogen survive, so if you imagine taking the secondary white dwarf and kind of uniformly mixing it and spreading it out, there is a very small amount of hydrogen that basically does remain cool for the whole time. And so I do think you can explain these kind of 10 to the minus 10 scale hydrogen layers as being able to keep that much material cool.
It's just material, so it's not connected. There's no mixing process connecting it to hotter regions that would destroy it. Yeah.
Exactly. So you imagine having a small amount of material that just manages to stay cool. I mean, I think this is somewhere that is kind of quantitatively difficult because a lot of the merger simulations don't really follow the hydrogen and helium layers in detail. And so, you're kind of picking the hydrogen distribution a little bit by hand afterwards. But if you imagine saying that it's uniform, you can keep, I do think you can keep small amounts in material that just remains relatively cool. And then especially in these very high surface gravity white dwarfs, pretty quickly get it segregated to the surface.
Okay, thank you.
Great. Let's go with Nicole.
Yeah, hey, I'm wondering for how long would you expect that circumstellar material from the merger is visible? And also, would you always expect it to be hydrogen and helium deficient?
Yeah, so I think you almost always expect this material, circumstellar material, to be hydrogen deficient. It needn't be helium deficient. I think in particular, if you imagine that you have a helium white dwarf merger, that you could well have expelled helium material. And I know the R-core Bohr stars show evidence of circumstellar material, and that's somewhere where, again, I would not expect it to be helium poor. Exactly how long that persists is a little unclear to me, but I wouldn't expect it to be, much longer than kind of planetary nebula timescales. So by hundreds of thousands or millions of years, I expect that to be gone. So I think on the cooling track, there's probably not a whole lot of hope for circumstellar material.
Yeah, but you said the Bohr stars stay there for 10 to the 6 years.
Yeah.
And the typical planetary nebula timescale is 10 to the 5 years. So yeah, it would be gone already when they approach the hot temperatures.
Yeah, so that may be true. For something like the R-core Bohr stars, where there are still continually shedding mass during that phase, I don't know whether then there can still be material around them. I'm actually not exactly sure what the observations say about circumstellar material in the extreme helium stars, whether there is any material being lit up there.
No, what was not yet discovered.
Okay.
Roseanne.
Hi. In terms of the origin of the stars that merged, you had, of course, mentioned that they could be a very tight white dwarf binary.
Yes.
Is it ruled out that they could also have merged within a common envelope?
No, I don't think I would not describe that possibility as ruled out. Yeah, the population I'm thinking of is just, say, taking the known currently detached systems and evolving them forward. But I think there are opportunities for objects produced via other merger channels, and you could have something merging within a common envelope potentially.
Thanks.
Tom, since you didn't get to ask a question before.
Thanks. The spin periods of the systems you identify seem quite long. I mean, obviously a white dwarf could potentially spin much faster. Do you think they are slowing down after the merge, or is that reflecting the merger? Yeah.
So my own picture is as follows. So if you imagine following the merger, exactly as you say, Tom, both on, you can have much more angular momentum to be critically rotating on the cooling track, and you have a huge amount of angular momentum in the orbit at merger. But if you imagine following an object through this sort of evolution, and you ask, what is its moment of inertia? That moment of inertia actually reaches a minimum during this kind of luminous phase. And so I've tried to make the argument in some of my work that when you go through this phase, if you imagine shedding material such that you basically just never exceed critical rotation, then you have to lose a lot of angular momentum while you're large, essentially here, while you're kind of contracting from your giant radius phase down to something more compact. You ought to shed a significant amount of angular momentum. And if quantitatively, if you do that and say, I'm just going to hold things to be no more rapidly rotating than critical rotation through this evolution, it actually does very nicely imply kind of 10-minute periods on the cooling track.
Okay, thank you very much.
And one last question from Donnie.
Thanks. Besides a related question, when you see that rotation, how can you be sure that it's not really pulsations? Because the time scales are 5-10 minutes, like we saw for pulsations in Alejandro's talk.
Yeah. Oh, I do think that is something that you have to try to distinguish. I mean, some of these objects, sit in regions where we don't have an identified pulsation mechanism, and that leads senses that this is probably rotation. For some of the objects that have extremely strong fields, magnetism provides you a mechanism to have a non-uniform surface and also potentially suppress pulsations. But I do think one needs to be careful. Sometimes these are just sinusoidally observed periods, and exactly what that is physically does require some additional interpretation.
Thanks.
Jeff, is it a quick question? You can't answer me.
Yeah, it's pretty quick. I just wanted to add a quick statement that one of those white dwarfs, Josiah, that you mentioned, REJ0317,
yep, that
has a wide white dwarf companion at 200 AU.
Mm-hmm. Yes, definitely. So that has been, So the evolution of that system. There's a lot of writing in the literature in the last 25-30 years on that, and it has its share of puzzles for sure.
Great. All right. Thanks again to Josiah.